Now, I don't know if you can see those very well, but you'll see stars twinkling here. This is a globular cluster 47 Tuc in the southern hemisphere, and every one of those blinking, twinking dots is an RR Lyrae variable star. They used to be called cluster stars because they're found so often in globular clusters. And actually, these are very old stars. You find them in globular, they are population 2. Population 3 are the first generation stars that everybody's trying to find. Population 2 stars have a little bit more metallicity because they formed after the first generation stars. Population 3 went supernova, created elements, metals that got incorporated in the next generation of stars. So when they say population 1, 2, and 3, they are talking the metallicity. First generation stars with a population 3, they only had the elements originally that were that came into existence when the Big Bang brought the universe into existence. And then when they went supernova and they produced all those heavier elements as that happened, that incorporated into clouds of gas and dust, which then became incorporated into protostars, which then became the next generation of population 2 generation stars. So when they have a higher metallicity. And we're still talking less than 1%, okay? No matter what I say or what you think or what you read, do not forget, stars are 75% hydrogen, 24% helium, 1% metals, pretty much. So we're not talking huge amount of metallicity here, but it is enough to make a difference, especially with RR Lyrae stars. This is a deep sky object this year, globular cluster M15 in the constellation of Perseus. It too has a lot of RR Lyrae stars in it, and they are very, very important RR Lyrae stars when we talk about measuring distances in the universe. Now, there is also the RR Lyrae instability strip, where the stars, they've been on the red giant branch, they're transitioning off the red giant branch. They're very old stars. They're population 2 stars. There are no new RR Lyrae stars because it is thought that the very reason that they pulsate this way is because of their low metallicity. Thought. Remember, I keep saying we think, maybe, theoretically. We know very, very little about stellar evolution, the details anyway. When these stars, which were red giants, now they're old red giants, they go through this little period right in here where they pulsate, but this is a very different pulsation. It has this very unique curve. When you plot its change in brightness over time, very unique. If you see this light curve, that's an RR Lyrae star. If it's an RR Lyrae star, you know a lot about it. The period of pulsation for an RR Lyrae is less than 1 day. And they all are spectral class A, maybe a little bit F, so you know their luminosity. With those two things, you can use RR Lyrae stars to determine distances to other galaxies. So, once the star has fused carbon, it doesn't get hot enough in its core to fuse anything heavier, except every now and then. Pretty much stops with carbon. So now you have a carbon core, a stellar core of carbon, and around it you have what is called a planetary nebula. Because when it collapses for the final time, carbon can't fuse, it's not hot enough, the core does a slight little rebound, pushes the stellar envelope out into the interstellar medium, throws it away from the stellar core. And you have the white dwarf left in the middle, and you have the planetary nebula surrounding it. And you will see this bilateral shape. Actually, this is the youngest planetary nebula, NGC 2440. It's very, very young. It has this bilobal physiology. And these are 3 more examples of planetary nebula. There are so many planetary, they're stunningly beautiful, okay? However, they're very transient. When you see a planetary nebula, you know that that's only about 50,000 years old or so, okay? Because there's These aren't very massive stars to begin with, and 95% of all the material ends up in the core of the star, and it's only 5% that gets scattered out into the supernova remnants in the planetary nebulae. So it just keeps going further and further out and getting thinner and thinner until you can't see that anymore. So you can definitely see the difference that these are much older than this one because the planetary nebula has expanded further and further away from the white dwarf, leaving just the white dwarf behind. This is the ring nebula in Lyrae, and this is the southern ring, the 8-burst nebula. And this, just to show you, there are several different physiologies for planetary nebulae remnants. It depends upon the processes that the star is going through as it forms the planetary nebula. Lots of different situations can happen to a star going through this process. Or maybe the planetary nebula is expanding into a part of space where there's some stuff here but no stuff here. So it got to kind of get interfered with in one part. So you end up with all these different orientations. Plus, these would look very different if they were angled to us differently from our perspective here on Earth.